video, we are going to practice on the MCQs questions based on the planar graph, Euler's theorem, and chromatic number of the graph. Let's start with the first case. The number of regions in connected planar graph having 6 vertices and 7 edges. As per this question, we need to find the number of regions. And regions are calculated with the help of Euler's theorem. It states that if the graph is connected, planar as well as a simple, then the number of regions is equal to E minus V plus 2, where E indicates the number of edges, V means number of vertices. Also, region is called as the faces. If the question is number of faces or the regions, the meaning is same. In this case, number of edges are 7, vertices 6 plus 2. Simplify this. This is equal to 7 minus 6, 1 plus 2 is equal to 3. Hence, option C is correct. Next question. If G is a planar graph, then the chromatic number of that graph is what? Planar graph means if we have any graph that can be constructed without crossing of the edges. Suppose we have K4. That is a complete graph with the 4 vertices. As we have the intersection of edges here, can we reconstruct this graph without crossing of the edges? Yes. We will take the outer boundary as it is, take one diagonal as it is, and the second diagonal, rather than drawing from here, we can take from the outside. And here we have no intersection of the edges. Whenever we have such graph that can be reconstructed without crossing of the edges, that is called as a planar graph. Now, what is the chromatic number of the planar graph? Is this is always is equal to 3? No. Why? You can take this example, K4. In this case, what is a chromatic number? Chromatic number means minimum number of color used to color the vertices such that no two adjacent vertices have same color. Here, if I use the yellow color, I cannot give yellow to this vertex as well as this because all these three vertices are connected with this yellow color vertex. It means I need to assign a different color to these one. Let's suppose I color this vertex as the red. Now red color cannot be given to this vertex because that is connected with it. Even we cannot give red color to this because that is also connected by an edge. So we need to give the different colors to these one as they are also connected with each other. In short, total color 4 is used in this case. So that can never be is equal to 3. Is that is always 4? No. We can take some another graph. Let's suppose we have this graph. This is clearly a planar graph, no intersection of the edges. Here the chromatic number is not 4 as there are 3 vertices, and even if you calculate that, minimum number of color used in this case is 3 and hence its chromatic number is 3. So it cannot be a 4. Is that is always less than or equal to 3? No. And last option is clearly correct, and this is basically a 4 colorable theorem which states that every planar graph is 4 colorable. 4 colorable means maximum number of color used in a planar graph is 4. So if you know the theorem statement, you can directly answer it. Otherwise, we can consider different cases of the graph and we can identify what is the correct option. Next is the expression for the Euler's formula is what? Suppose you know the formula, you can directly mark the option. Otherwise, what we can do to answer this question, we will take any planar graph because Euler's formula is applicable for the planar graph. Here I have taken the C4. Number of vertices in this case is 4. Number of edges 4. Now how many regions we have in this case? Region means we need to take this plane and this plane is get converted into two parts. One is inside, another is outside. So total regions are 2. Now with this case, check which formula is true. Let's start with the first case. Is R is equal to this one? Vertices count is 4, edge count 4 plus 2. Is this is correct? Yes. Right now we are getting R is equal to 2. Now we cannot directly say that A is correct option. With the help of examples, we can discard the option. What about the second one? Is the vertices count is equal to h minus reason minus 2? No, here we are getting a 0, but vertices count as 4, so clearly we can discard the option B. For the C case, 4 minus 2 plus 2. This is also valid because that is equal to 4, and even in this case it is a 4. Now let's take one more example. If I take this case, it is a graph that contains the 4 vertices. Edges count is increased by 1, that is equal to 5. Even reason is right now 3. Outer reason, inside 2 reasons. So we have 3 reasons. Now check whether A or C is the correct option according to this. In this case, R is equal to vertices 4 minus edges 5 plus 2. Simplify this. This is 4 minus 5 minus 1 plus 2, that is equal to 1. Is the reason count as 1? No. So means we can discard the option A. Check it for the case number 3. Vertices is equal to h minus reason plus 2. This is equal to 2 plus 2, that is equal to 4. Is the vertices count as 4? Yes. It means option C is correct. Moreover, recently we have covered the case number of reason is equal to number of edges minus vertices plus 2. From here, vertices count can be calculated as this taken on the left side, that will be a positive V, E minus, in place of V we can write R plus 2, and that is the correct formula. Next we have the minimum number of color required to paint the falling graph is what? In this case, we just need to find the chromatic number of this graph. For this case, suppose I color this vertex as a blue. I cannot use blue here even in this case, but I can color this vertex as a blue because they are not adjacent. Now can I use blue color here? No, but we can use here because they are not adjacent. Now check it whether these three vertices are adjacent with each other. Not everyone, but here we can use, if red, we can also apply the red color to this vertex. But we cannot use red in this case because that is connected with this red color vertex, as well as we cannot assign it as a blue. So in this case we need to use a different color. Suppose it is a yellow. So total number of color used in this case is 3, and hence option C is correct. Taking the next case, the 4 colorable theorem to prove the planar graph is what? Whether it is a necessary or a sufficient condition. 4 colorable theorem says that the chromatic number of planar graph is less than equal to 4. Means if we have any planar graph, surely its chromatic number is less than equal to 4. But if it is a planar, it doesn't mean always 4 is there, always 3. Or if the chromatic number of any graph is 4, then we cannot say that it is a planar graph. Because if we take the case of K33, that is a complete bipartite graph, the chromatic number of this one is 2 because we can assign a same color to these vertices but different from this one. So its chromatic number is 2. As we know that a complete bipartite graph K33 is not a planar graph, then it cannot be concluded directly from the chromatic number. So remember that the 4 colorable theorem is neither a necessary nor a sufficient condition. Based on this one, let's take one more example. All the planar graph have chromatic number less than or equal to 4. This is the same statement I have stated here. So this is true. Since all the complete bipartite graph has a chromatic number 2, that is the reason that all the complete bipartite graph are planar. That is completely incorrect. What is the incorrect in this case? Chromatic number of the complete bipartite graph is always 2. It's very clear because it is a bipartite graph and the chromatic number of it is always true. But with this statement, we cannot say that it is a planar graph, as we have the counter example complete bipartite graph K33. It is not a planar graph. It means the statement is incorrect. So according to this, option A is correct. Statement 1 is correct, but not the statement 2. Taking more examples on the chromatic number, what is the chromatic number of the cycle Cn where n is odd and n is greater than or equal to 3? Cycle Cn. So let's start with the C3 first because we need to take the odd number. Minimum number of color used to color these vertices, that is 3. Now let's take C5. In C5, let's suppose we color this vertex as a green. Now we cannot color these two vertices as a green, but we can color any one of them as a green. Let's suppose this vertex is colored by the green. Here, if I color red, it means I can color this vertex as a red or this vertex as a red. Let's suppose this vertex as the red. In this case, we cannot color this vertex as a green or red. So surely we need to take the different color. Let's suppose pink. So total color used in this case is again 3. So in C3, total number of color used is 3. So its chromatic number is 3. For C5, again 3. So if you take the C7, clearly in that case the chromatic number is 3. So in short, C option is correct. Taking one more case, the chromatic number of Qn. Now what is a Qn? Qn is NQ. So we need to remember the three structures of the Qn. One is Q1, another is Q2, and the third is Q3. Q1 means it consists of the two vertices and the name of vertices is 0, 1. Q2 is of the form square and this vertex we can label 0, 0. This is the 0, 1. Here 1, 0, 1, 1. Q3 is actually a cube where vertices representing the width string of the length 3. Now let's derive the chromatic number of Qn with the help of these three cases. Here the chromatic number is 2 because two vertices are there and they are adjacent. In this case, if I color this vertex as a red, then we cannot assign red to these vertices. But we can assign red to this vertex. So clearly we can assign a different color to these one and let's suppose green. Chromatic number again is 2. Let's identify for Q3 whether the chromatic number is 2 again. Suppose this vertex is of the green. Now I cannot give green color to this, even to this as well as this. But we can assign green color to this vertex. Same for this. Can we assign green to this? No, because that is adjacent with the green color vertex. But we can assign green color to this vertex. Now think for these four vertices. Whether these four vertices are adjacent? No. So there is a no edge between these two ones. So we can color same as the red. Between these two ones? No. So we can assign the same color as a red. And same for this. So the chromatic number of Q3 is also 2. In short, the chromatic number of Qn is 2. The next question is, in the complete graph K5 with the 5 vertices, whether the Euler's theorem is satisfied and then we can count the number of regions or not. As per these one, we just need to figure out whether the graph is planar or not. Remember that in complete graph where Kn, n greater than or equal to 5 are the non-planar graph. Here we have the number of vertices as a 5. It means surely K5 is non-planar graph. And the Euler's theorem is applicable only for the planar graph, not for the non-planar graph. So clearly option A, B, C all are incorrect. Only D option is correct. So the base is a planar graph and then we can move to the Euler's theorem. Even if you are going to apply the Euler's theorem for the K5, that is not applicable because there is an intersection of the edges. You will not get a planar representation, then how we can calculate the number of regions there?